I will start with the definition of phase. And as you know, and this is well known if you have studied physical metallurgy and you have looked at phase diagrams, then I'll define phase diagram and how what are the principles behind phase diagram. These will be described in this course, but you might have seen some phase diagrams, whether it's a unary system or a binary system. You might have seen some phase diagrams, but what is a phase? This also we know. It's a portion of matter that is chemically uniform, physically distinct and mechanically separable, right? This is something a textbook definition, right? It is given that it is chemically uniform, physically distinct and mechanically separable, right? But I can also define the phase as a subsystem of a composite system. If you remember, when you define a composite system contains subsystems, but overall the composite system is isolated. It is isolated from the surroundings, but it has several subsystems, and these subsystems are separated by walls, and each subsystem is characterized by its own internal energy, volume and mole number of species, right? So basically you can think of phase as a subsystem. So again, if I think of phase the way another definition of phase, it is portion of a thermodynamic system, right? Instead of telling portion of matter, I am telling that it's a portion of a thermodynamic system throughout which properties such as density, chemical composition, magnetization, heat capacity, these type of properties are uniform. So it's a portion of a thermodynamic system. Instead of telling it's a portion of matter, I am talking of it as a portion of a thermodynamic system. So as a result, what happens is, with these ideas, see, phase is a subsystem of a composite system or portion of a thermodynamic system, you can immediately identify the previous idea, the concepts that we have been given of thermodynamic equilibrium that has been given in terms of subsystems of a composite system. So it's a portion of a thermodynamic system, means it's a subsystem throughout which properties such as density, chemical composition, magnetization, heat capacity, electric polarization or susceptibility, these are uniform. So these should have physically and chemically distinct properties, right? So a phase has its own composition, for example, right? So that is exactly what I am talking about. And if there are two phases, say in a microstructure, in a material, you often see these internal structures under a microscope. In these internal structures, you see different types of contrast. Now, and so these contrasts are often identified as phase. Now, if you see, when you see the contrast, the main thing that distinguishes these two phases is the phase boundary or the interface between the phases, right? Now, if you think of a phase boundary, the phase boundary is drawn here. It's like a hypothetical phase boundary, or you can think of it as a physical phase boundary. So, right. So basically, if you look under a microscope in a system, say in an eutectic system, you will see that there is these two different phases like cementite and ferrite, and there is a distinct phase boundary that you can identify that separates these two phases, right? So this is one phase boundary I have shown schematically, and if you look at that, you have on one side alpha phase, another side beta phase. How is alpha phase characterized? It will have rho alpha, which is uniform throughout. It will have heat capacity, okay, which is again uniform throughout. Then it will have some magnetization, say for example. It will have also mole fractions of different components that make up this phase, like x1 alpha, x2 alpha and so on, right? It will also have its own energy, its own molar volume, etc., etc. Similarly, our lattice parameter, again phase beta, like it has its own density, we can think of, and it has its own molar volume, so therefore it has its own unique lattice parameter. And then you have phase beta, say again phase beta has a unique density rho beta, it has a unique heat capacity Cp beta, then unique magnetization. Say for example, iron chromium system, the iron rich phase is magnetic while the chromium rich phase is not. So as a result, you have now again, so the chromium rich phase, when we identify a chromium rich phase, one of the characteristics that we see is that it has no magnetization, right? But if I look at the iron rich phase, on the other hand, I look at that, I see that it is ferromagnetic and it has a spontaneous magnetization associated with it. Again, chromium rich phase has more chromium and the iron rich phase has more iron, and throughout the phase the composition of iron will more or less be uniform. Again, throughout the phase, for beta phase, x1, x2, x1 beta, x2 beta, these will be uniform, right? So basically it will be chemically and physically uniform in terms of chemical and physical properties, right? And it is mechanically separable. Now, when we talk about phase transition, one of the common phase transitions that come into that immediately come to our mind is like water evaporating, right? Water boiling and it turning into water vapor, or water freezing and becoming ice, or ice melting and becoming water, and so on, right? So basically this is or some phase alpha transforming. So basically the idea is some phase alpha is transforming to beta. And then when we look at phase transition, we also characterize something called a phase transition temperature. Phase transition temperature and pressure. Now when we talk about phase transition temperature and pressure, what we are telling is that there is a given pressure and given transition temperature at which alpha can transform to beta, or vice versa, beta can transform to alpha. In one case, say for example, for alpha to beta conversion, alpha may require heat from outside, while for beta to alpha conversion, heat can be released to the surroundings from the system, right? So this is so as you can see, there is this arrow that is moving from alpha to beta. There is another arrow which is from beta to alpha, and as you can see, at the phase transition temperature and pressure, this alpha beta conversion can go either way. So that means it is reversible, right? So there is a phase transition temperature and pressure. Now I told that whenever there is heat transfer or heat exchange between the system and the surroundings, if there is a heat exchange between the system and the surroundings, say some delta Q is added to the system or delta Q is removed from the system, you will always have a corresponding entropy exchange, right? There will be an entropy exchange, right? So this is called entropy transfer or entropy exchange between system and surroundings, right? Now think of an internal process like this phase transition, internal process such as a phase transition inside a system. Now if this internal process is spontaneous, or natural or irreversible, then there will be also a non-zero entropy produced. So there is entropy exchange between the system and the surroundings due to heat transfer, but there is also entropy produced inside the system, and there can be also entropy produced inside the surrounding if there is some process happening in the surrounding. But the entropy produced, so if I am considering only an internal process which is happening only inside the system, then entropy produced is called DSIR or DSP. That means this P means entropy is produced, right? Entropy production, or entropy that is happening due to this irreversibility. Irreversibility is associated with any natural or spontaneous process. So any natural or spontaneous process will produce some entropy. So there will be some entropy that is coming from the exchange between system and surroundings. It is like an exchange of thermal matter. If you remember, it is like an exchange of thermal matter, and that exchange of thermal matter is due to heat transfer. And if there is this exchange of thermal matter when there is a temperature gradient, for example, that part is, you will see that part can always happen if there is a heat transfer. Whether it's a reversible process or irreversible process, that is immaterial. However, when the process is irreversible, then there will be also a non-zero entropy produced. This is the most important part. So basically, if I go further, so if I describe further, so this DSIR will be equal to 0 when the process is reversible, right? When the process is reversible. Now first law, when we talk about, if I think of these quantities like dV, right, there is a dV or dN as exchange quantities, like exchange between the system and the surroundings. For example, dVE is the change in volume of the system or volume exchange between the system and the surroundings. Again, dNE is basically nothing but change in amount of component inside the system or matter exchange between system and surroundings. This can happen when the system is open. In the DVE, it can happen even when the system is closed, right? You can have mechanical energy transfer or energy transfer when the system is closed. But DNE or matter transfer between the system and the surrounding can only happen when the system is open. Or we are considering a subsystem which is separated by a permeable membrane, which is permeable to the exchange of matter or exchange of species. Right. So now, if I look at this internal process that is happening inside the system, and I rewrite the thermodynamic, the first law, it is the combined first law, second law. Then what I'll write? I'll write T dSE minus P dVE plus mu dNE, which is nothing but for a reversible process. This is same as TdS, that is change in entropy, minus P dV, that is change in volume, and there is multiplied by pressure. And as you remember that U as a function of SVN, you have expanded and you have written this coefficient. So D equal to TdS minus PdV plus mu dN, right? So this is signifying a reversible process. However, and for reversible process, you have only exchange terms. But for an irreversible or a natural or spontaneous process, we have told that there is a DSIR, which is greater than 0, right? So it is like a DSIR. In this case, if it's an irreversible process is happening inside the system, then DSIR system has to be greater than 0, right? If it is happening in the surrounding, then DSIR surrounding also has to be greater than 0, right? Wherever there is an irreversible or spontaneous or natural process, natural process or spontaneous process or an irreversible process, they are all same, right? If there is a natural process, there is a natural reaction to the process, and the process will happen spontaneously or irreversibly, right? So DSIR system in that case will be greater than 0. Now if you see, if I now rewrite the first law, taking into account this irreversibility component, then DS exchange, that is the amount of entropy exchange between the system and the surrounding, is nothing but DS of the change in entropy of the system overall. DS sys means this is like a DS system. So basically what I am trying to say here is DS system, which is equal to DS, is nothing but DS exchange plus DSIR, right? So if that is so DS exchange is nothing but DS minus DSIR, right? DS minus DSIR, right? So that's what I am writing. DS equal exchange now becomes equal to DS minus DSIR. Now if that is so, then we can write du in the case of an irreversible process happening inside the system equal to TdS minus PdV plus mu dN, and DS exchange, this DS exchange term is what? DS total change in entropy minus the irreversible part, right? So DS minus TdSIR, right? So that is the idea, and this is something that has been used. This TdSIR has been used in by Hillard, right, in his phase diagrams, phase transformations book. Recently by Longking Chen in his book on thermodynamic equilibrium and stability of materials. It is to basically understand and also quantitatively explain the quantitatively calculate the contribution of the entropy that is produced in the system when there is an irreversible process, right? So you have this equation now. Whether process is reversible or irreversible does not matter. This equation tells you the change in internal energy of the system equals to TdS, that is the change in entropy, times the temperature. By the way, temperature and entropy are conjugate variables. Then minus PdV, this is the mechanical work done, the reversible mechanical work done, and then is mu dN. By the way, there is this TdSIR. Now this entropy produced can be because of irreversible exchange of mole number, can be because of some irreversible exchange of pressure. It can happen for various reasons, right? So, but there is this T minus TdSIR, and that is because of the entropy that is produced in the system if the process is irreversible. Now, this TdSIR we often write as TdSIR can also be written as shown in Hillard's book, or Long Chen's book, that it can also be written as d zeta, where d is the amount of dissipation of internal energy, right? Or this is basically driving force. This amount of dissipation of, again, as I told you previously, entropy basically measures the dissipation of the internal energy, right? So basically the amount of dissipation of internal energy, or you can think of this as a driving force for a spontaneous or a natural or an irreversible process, right? For example, heat flow from hot body to a cold body is a spontaneous or natural or irreversible process, right? It has to be a natural process because it does not require any engine, right? It does not require any external work to be done or stuff. So you have a hot body, you have a cold body, you put them together, heat will flow spontaneously from a hot body to a cold body unless there is equilibrium established, right? So now zeta, what is this zeta? So instead of TdSIR, I am representing by dd zeta. In those books, in the books they use xi, but I am using zeta here. So zeta is the extent of the process. The extent of the process means zeta is some sort of an internal process variable or an order parameter. You can think of it as an order parameter or an internal process variable. This basically tells basically if I tell it's the extent or progress of the process, say I am tracking the progress of process. So at the start of process, zeta is equal to 0. At the start of process, zeta equal to 0. Now, as I go to the end, my zeta increases, and at the end of the process, once the process is completed, then zeta becomes 1. Right? So that is how we can define zeta, which is an order parameter which quantifies the extent of the process, or it is an internal process variable which tracks the progress of a spontaneous process. Now remember, the driving force is equal to 0 for a reversible process. There is no driving force. Alpha can transform to beta, beta can transform to alpha when it is a reversible process, right? If it's a reversible phase transition, alpha can transform to beta, beta can transform to alpha. For example, at 1 bar pressure and 0 degrees Celsius, like 273 Kelvin, ice to water transformation is a reversible process because ice can transform to water, water can transform to ice, right? It's a reversible process. However, D becomes greater than 0 for an irreversible or spontaneous process. And as I told you, TdSIR is written as dd zeta. And D is given as, now this D variable, there is the driving force or the extent of dissipation is given by, or amount of dissipation of internal energy, basically which produces this irreversibility, is given by minus del U del zeta and at constant entropy, volume and mole number, right? It's called minus del U del zeta. So as I was telling you, this is zeta is like an order parameter in a phase transition process. Now zeta equal to 0 in the, so basically if I tell zeta equal to 0, that is the parent phase. Now if zeta lies between 0 and 1, it's a mixture of parent phase and product phase. For example, there is some phase transition that is happening from a cubic phase to a tetragonal phase. Then when I am talking about cubic phase is the parent phase where zeta equal to 0. Now there is a value of zeta between 0 and 1 which basically signifies a mixture of the parent phase and product phase. And zeta equal to 1 is basically the product phase. Zeta equal to 1 is the product phase. Right? So now if we have that, if we know this DSIR and minus TDSIR, now DSIR is nothing but d by t, d zeta, right? According to this definition, DSIR is nothing but d by t d zeta. Now d by t d zeta, right? So according to this definition, it follows that DSIR equals to d by t d zeta. And now if I integrate from the initial state to a final state, remember, this is another very important point that I want to tell you. If I have 2 points, see, the advantage of using state functions is that we are only interested in the 2 states. What is the path followed? Whether the path is irreversible or reversible, it does not really matter, right? As long as I know the 2 states, I know the properties of these 2 states in terms of entropy change or internal energy change, I can quantify the amount of entropy produced or amount of some quantity consumed and stuff, right? We require, for state functions, we only require the final and the initial states. We don't require to know how this initial to final state transition has happened. whether through a irreversible path or through a reversible path, right? So we don't require to know. Now, if you see, when I am integrating, this is like d by t d zeta, means I, instead of writing initial to final dsir, I can also do a d by t d zeta, but d zeta, zeta signifies the extent or the progress of process, or zeta is an internal process variable, or it's like an order parameter. When there is, when cubic and tetragonal phases are coexisting, then the order parameter is between 0 and 1. When it completely becomes the product phase, that is the tetragonal phase, then zeta becomes equal to 1, otherwise zeta equal to 0, right? So that's how you can define a cubic to tetragonal phase transition. Means a lattice, a solid lattice, a solid is transforming from cubic phase. Cubic phase means it has a cubic crystal structure. Then at a certain critical temperature, for example, it changes from cubic crystal structure to a tetragonal crystal structure. It can be because of certain temperature, it can be also because of some application of certain strain, that you get such a transformation. Again, you can think of liquid to solid transformation the same way, or when it is an irreversible process. For example, if I take some ice in water and then I take it to room temperature from 0 degree Celsius, from 0 degree Celsius I take it to room temperature, then that ice that is there, or the ice cubes that we have put inside water, these ice cubes will start melting, right? So they will start melting and they will melt irreversibly and they will produce water. So I am at room temperature, say 25 degrees Celsius, and I have a bucket full of ice, and this ice bucket, ultimately once we will see that the ice bucket has converted to water completely. All the ice in the bucket have converted to water, right? It has melted to water. So that's an irreversible process. Now, how much is the amount of irreversibility? This type of definition will help us quantify, right? So again, if so now think of an isolated system. If I have an isolated system means no way there is any exchange of energy, means it does not allow exchange of energy, it does not allow exchange of volume, it does not allow exchange of matter, right? Isolated system does not allow any exchange whatsoever. Now, in such cases, D can be written as T del S del zeta, right? It can anyway be written as T del S del zeta. Now, if you see here, so for such a process, for an isolated system, D can be 0 if the initial state inside the isolated system is at equilibrium. If the initial state is at equilibrium, then D is equal to 0. That means there is no driving force for any spontaneous process, because you are already in the equilibrium state. However, if you are away from the equilibrium state, that means you have an initial non-equilibrium state, then D has to be greater than 0. Right? So for a closed system that is in contact with, say, a thermal and mechanical reservoir. For example, now if it is thermal and mechanical reservoir, we know from the Legendre transform that instead of using this potential U, instead of using U as Vn, we will try to use G, or Gibbs free energy, as a function of temperature, pressure and mole number. So S and T are conjugate, so S will be replaced by T, S is replaced by T, and V is replaced by P, and N remains N. So this is now, so we use GTP. Now if you see, what is DSIR? DSIR is DS minus DS exchange, right? Now DS exchange is nothing but del QP by T, again a mechanical reservoir, so del QP by T, and du, and del QP is nothing but du plus PdV, right? Du plus PdV, which is nothing but, so the heat transfer at constant pressure is nothing but change in enthalpy. So you can configure it as change in enthalpy, since dP equal to 0, right? Now, so this can be written as ds minus delta Qp by T, or ds minus del dH by T, and this is, which is nothing but, if I take this, if I simplify this further, I can write T comes here, so T ds minus dH by T. But if you see, G is nothing but H minus Ts, right? Again from the Legendre transform, G is H minus Ts. So dG equals to dH minus T, ds minus S dt, but this is in contact with the thermal reservoir, so this is a fixed temperature, so dt equal to 0, so dG equals to dH minus Tds. If you see, Tds minus dH is nothing but minus dG. So ds IR is nothing but minus dG by T, which is equal to d del zeta d dt zeta by t, right? Zeta is again the internal process variable. So driving force is negative derivative or partial derivative of Gibbs free energy with respect to the internal process variable at fixed temperature, pressure and movement, right? So and the delta G, that is the free energy, the change in free energy for this entire process, for this entire spontaneous process, is nothing but a negative of the T into delta S, right? So minus T delta S IR is nothing but, that is the amount of extent of dissipation, right? Extent of dissipation of internal energy is nothing but delta G, right? Minus T delta S IR in this equation, in the equation that I showed here. So if you see, this entire term is nothing but, in this case, in the closed system which is in contact with the mechanical and thermal reservoir, it is nothing but delta G. That is not changing the Gibbs free energy, right? Now we take an example, a quick example. In fact, I have given this as one of the assignments and I have also explained there. I think that most of you have done it correctly. So if you see, you have, means a part of the problem has been given as an assignment. Right now, I will just discuss this problem in the light of this new stuff that you learned, that delta H fusion equals to, and as you know, delta H fusion and delta H melting are synonymous, right? And opposite of delta H crystallization or delta H solidification, right? So so the enthalpy change due to solidification is minus of the enthalpy change due to fusion or melting, right? Melting or fusion are the same process, right? So it is the, so if you think of the definition of delta H fusion or delta H melting, that is the amount of heat absorbed, right? A solid has to absorb this amount of heat, right? And 1 mole of solid absorbs this amount of heat, that is delta H fusion, that is nothing but the latent heat. So latent heat, and it converts to convert to 1 mole of liquid at 1 bar pressure. So delta H fusion is given again at the transition temperature. Remember, when I am talking about, when I am signifying, when I am telling that delta H fusion or delta H melting, that is the latent heat of melting or latent of fusion, and that is always specified at the given temperature. That given temperature is in general the transition temperature and 1 bar pressure, right? And as I told you, delta H crystallization, this is basically when liquid is transformed to solid. Now when the liquid transforms to solid, it releases heat to the surrounding, right? It releases heat to the surrounding. So it is the amount of heat released from the system to the surrounding when 1 mole of liquid solidifies or crystallizes to form 1 mole of, so 1 mole of liquid solidifies to form 1 mole of solid at 1 bar pressure. Let us call it 1 bar pressure. Sometimes people do use 1 atmosphere pressure, but let's call it 1 bar pressure, right? So in this case, I am thinking of ice to water conversion. Now ice to water conversion, the transition temperature or the temperature of the reversible process is 0 degrees Celsius and 1 bar pressure, right? 1 bar pressure means 10 to the power 5 Pascal pressure, and this is an ice. So at this temperature and pressure, ice to water transformation or transition is reversible, right? Ice can go to water, water can, means it can at 0 degrees Celsius and 1 bar pressure, water can exist in the solid state as well as in the liquid state, right? Both are in equilibrium, right? Ice and water are in equilibrium, right? And this, when ice and water, that means their free energies are equal, right? Ice and water free energies are equal. Now in such a case, ice can transform to water or water can transform to ice. There is no spontaneity, means there is no spontaneous transformation from ice to water or water to ice. However, if I raise the temperature above 0 degree, ice will melt to water spontaneously. If I lower the temperature below 0 degree, water will transform to ice irreversibly, right? So that is the problem. So how much is that is what we will quantify, right? So in this small example. So as you know, again, this is the combined first second law when we are talking about some process which can be a natural process or a reversible process taking place within a system. And again, we know all this math, and we quickly go through this, and what I am trying to say, that at constant pressure dP equal to 0, and then dH is du plus pdV, which we know. So we can write dH equals to TdS, right? From here, dH equals to TdS plus mu dN minus, right, TdS plus mu dN, because du plus pdV is dH, right? dH equals to TdS plus mu dN. Because what I have done is I have taken this here, so this becomes du plus pdV, and that is equal to dH. right? So once we have done that, now we are telling that, and the melting point, right, or melting point or freezing point is 0 degrees Celsius, right? That is the critical temperature, right? The phase transition temperature. So this is the phase transition. So 0 degrees Celsius is the phase transition temperature from solid to liquid or liquid to solid. Associated with, so phase is 0 degrees Celsius at 1 bar pressure. Remember, at 0 degrees Celsius and 1 bar pressure, ice to water conversion or water to ice conversion are both possible, because ice and water are in equilibrium and the process is a reversible process. Now we also define the molar volume of ice, which is 19.66 centimeter cube per mole. It is per mole, and of water is 18.02 centimeter cube per mole. Note that the molar volume of water is smaller than that of ice. What does that mean? What is the molecular weight of water? Molecular weight is 18.02 grams per mole. So if that is so, then rho is equals to 18.02 grams per mole by, now if I think of raw water, it is 18.02 centimeter cube per mole, which is equals to 1 gram per cubic centimeter, right? So density of water is 1 gram per cubic centimeter. So rho water, so basically rho is equals to m by Vm for any material, right? Now for ice, what it will be, ice and water, they have the same composition, right? Chemical composition is water, H2O, right? Which has a molecular weight of 18.02 grams per molecule, right? So if you have that, then rho ice equals to, this is here, it will be Vm is 19.66, right, and here it will be 18.02. So this comes out to be, I think, approximately 0.916. Say this is gram per cc or cubic centimeter. So gram per centimeter. As you can see, ice at this so at 273 K and 1 bar, that is 273 K means 0 degrees Celsius, right? 0 degrees Celsius is nothing but 273 K, and at this temperature and at this pressure, the dense ice is lighter than water, right? Now amount of heat released per mole of water, per mole, so amount of heat released when water solidifies to ice per mole is given by delta H crystallization, which is negative of delta H fusion, which is given as, say, negative of delta H fusion, and delta H fusion is 6006. Say let us assume delta H fusion equals 6006 joules per mole. So delta H crystallization is nothing but minus 6006 joules per mole. Now delta H is delta U plus PdV. Now delta U plus P delta V is nothing but QP, and QP is the heat transfer at constant pressure, right? Heat input to the system at constant pressure, which is nothing but equal to T delta S, right? Now the entropy released, now if you think of entropy released, because see, water transforming to ice means heat is released to the surrounding, so there is an entropy released to the surrounding, and that amount of entropy released will be minus 6006 by 273. So first of all, the heat released is minus 6006 joules per Kelvin, right? It is minus 6006 joules per Kelvin, and the entropy released is basically coming from this equation, Q equals minus Tm delta SE, right, which is basically given by minus 22 joules per Kelvin. Now if that is so, if there is an entropy released, right, so basically there is an entropy exchange, so inside the system entropy gets reduced, right, entropy gets reduced when water converts to ice, right? There is this delta SC is minus 22, right, delta SC is minus 20. That means in the surrounding, because it is released, there is a negative of delta SC, that is basically, so because the delta SC system plus delta SC surrounding should go to 0, right? Delta SC system plus delta SC surrounding should go to 0. So delta S surrounding is nothing but minus delta SC, which is 22 joules per Kelvin. It is also understandable because there is heat released to the surrounding, and as a result the entropy of the exchange, the amount of entropy that will go up in the surrounding will be like will be the same as the entropy that is transferred to that is the entropy that is changed in a system, right? This is due to the heat transfer, right, of 6006 joules per joules, and that's minus 6000. The 6006 joules is the amount of heat that is released by 1 mole of water when it converts to ice, right? Now 6006 by 2273 is the delta SC, but it is negative, right? It is minus Tm delta SC because entropy is released from the system, so to the surrounding. So the entropy of the surrounding will go up, and that will go up exactly by the same amount, so it is 22. So that delta S surrounding and delta S system, they add up to 0. So delta S is delta S system, which is nothing but delta SC, which is minus 22 joules per Kelvin, and this plus 22 joules per Kelvin. Again, remember this is all calculated per mole, right? We have taken 1 mole of ice, and I am looking at 1 mole of ice converted to water, or 1 mole of water converted to ice. Here we are looking at 1 mole of water converted to ice. Now if you see, you have delta SC, which is minus 22, you have delta SIR, which is delta S minus delta SC, which has to be 0. So for a reversible process, the irreversible component of entropy, or the entropy produced, has to be 0, right? And so you have now this delta S total, which is delta S system plus delta S surrounding, which is basically 22 at plus 22 in inside the surrounding, right? Inside surrounding it is plus 22, so I should have written this way. Minus 22 plus 22, which is equal to 0. So delta S total, that is the total entropy change, is 0. See, for a reversible process, entropy is conserved, right? The process is reversible, right? There is no change in total entropy, right? If a process is irreversible, there will be a positive change in entropy. But if the process is reversible, then delta S total, that is the system surroundings, or this is also called delta S universe. Universe includes system and surrounding, which is equal to 0, right? Now we have been asked to calculate the change in enthalpy, or the difference in enthalpy between water and ice at 273 K and 1 bar pressure. So water to ice is basically nothing but, see, delta H. So when I write delta H water to ice, water transformed to ice, what I mean is, it is H ice minus H water. Again, this H means I can use small h, or even if I tell 1 mole, then small h or capital H doesn't matter. So it is basically the enthalpy per mole. So is H ice minus H water, right? So basically delta H fusion will be H water minus H ice. So delta H water minus delta H ice, H water minus H ice, that is basically is nothing but delta H fusion ice to water, right? So ice has to absorb it, so it is minus of the delta H distillation, so which is equal to delta H fusion, which is nothing but 6006 joules. Now if you look at the molar volume, then you can also estimate U water minus U ice, because H water minus H ice is nothing but U water plus PV, P into molar volume of water, because I am talking about one mole of water, and convert it to 1 mole of ice, and this is U ice plus PVM of ice, which is equal to 6006 joules. Now we can calculate PVM water minus PVM ice. P is given. P is basically 1 bar, which is like, think about 1. It can be 10 to the power 5. I mean, sometimes you can also use 10 to the power 5 Pascal or 101325 Pascal, and then you have this difference 19.66 minus 8.02, and this is centimeter cube per mole. So you can convert it to meter cubes, which is 10. You have to multiply by 1 meter is 100 centimeters, so you have to multiply by 10 to the minus 6. So what you get, the contribution that you get, if you see, these are both condensed phases. See, there is no gaseous phase. So the PV work is really small compared to the enthalpy of fusion. See, the enthalpy of fusion or heat of fusion is 6006, whereas this PV work, the difference in the PV in water and ice for this pressure, 1 bar pressure, is only 0.166. So 6006 plus 0.166 is basically, this is like the numbers in thousands, and it is like numbers in tenths, and so 6006 plus 0.166 is actually 6006.166, but that 0.166 is negligible compared to this number, right? So we can take same, that means PV work I can neglect, right? Now if that is so, another thing that we are talking about, S water minus S ice. So S water minus S ice is basically delta S. So it is basically delta S ice to water. Obviously, again, common sense tells us that ice, which is solid, will have lower entropy than that of water, right? Water, which is liquid, which will have more, right? Which will have more mobile atoms, and which can slide past one another, which can slide be slightly more disordered than solid. In solid, it is very closely packed compared to water. Then you can immediately see that S water minus S ice is nothing but the amount of entropy that was produced in the that was changed the system during this reversible process. We should not use the word produced. That the amount of entropy that was required for this transformation to take place was 22 joules per Kelvin, right? 22 joules per Kelvin was the amount of entropy that happens to exchange, and that is 22 plus 22 happens as surrounding, and plus minus 22 happens in the system. But in this case, this is ice to water, right? So basically, ice to water means ice will require heat. So heat is coming inside the system. If it is coming inside the system, there is a change. There is also thermal matter coming inside the system. That means the entropy is increasing, right? Although there is no irreversibility, but the entropy is increasing, and the entropy difference is nothing but plus 22, right? It is plus 22 joules per Kelvin inside the system. Now, think of one interesting case. Now see, this is basically I am looking at. So if you look at, I am actually developing thermodynamics for a unary system. Unary means one component system. Water is a single component, right? We are not talking about hydrogen and oxygen, because we are not caring about that reaction of hydrogen and oxygen combining to form water. We are just looking at phase transitions in water, and water is a single component. As a result, a single component system, we are looking at phase equilibrium in a single component system. And the equilibrium that we are specifically looking at is the equilibrium, solid liquid equilibrium, that is coexistence of ice and water at 273 Kelvin and 1 bar. Now let us consider irreversibility. That means we will consider the temperature at which the process of converting from water to ice or ice to water becomes irreversible. Now if that is so, if we consider 298 Kelvin and 1 bar, 1 mole of ice in this case is irreversibly melting to 1 mole of water, right? 1 mole of ice is irreversibly melting to 1 mole of water. Now think of enthalpy difference and entropy difference, that is H water minus H ice, or and S water minus S ice, basically to be the same as that of 273 Kelvin, right? That is the same as that of, so at 298 Kelvin we are telling that the change is, it is very insensitive, that H water minus H ice or S water minus S ice, the change in with respect to temperature is very small, right? That basically the Cp contribution is small, is what we are talking about, right? So the enthalpy difference and entropy difference do not change, they are same as that at 273 Kelvin and 1 bar pressure. At 298 Kelvin and 1 bar pressure, it is the delta S melting, right, per mole, and delta S melting per mole at 273 Kelvin and 1 bar pressure are the same, and that is equal to 22 joules per Kelvin, right. The system requires 22 joules per Kelvin for this conversion or this transition to take place. However, note this, that at 25 degrees Celsius, this is an irreversible transformation. Now, when ice melts, heat is absorbed by the system from the surroundings. Now, so in the surrounding, from the surrounding, so if there is a negative heat input to the surrounding, right, heat is getting absorbed, right, so it is coming from the surrounding, so which is basically, now surrounding is at what temperature? 298 Kelvin. How much of heat is required? That is enthalpy is required, it is 6006, right. So when ice melts, it requires 6006 joules, right, per mole. So in 1 mole it requires 6006 joules. Now minus 6006 by 298 is the temperature of the surrounding, right. It is because 298 is the temperature of the system, so it is the temperature of the surrounding also, right. So 290, because system and surrounding should have the same temperature at thermal equilibrium. So then delta S surrounding is minus 20.15 in this case, because heat is transferred from the surrounding to the system, right. So that entropy or thermal matter of the surrounding goes down, right, but it goes down by minus 20.15. But the amount of heat, that entropy exchange that is required for ice melting to water is basically plus 20.15 joules per Kelvin, right. So the entropy exchange during ice melting to water, right, ice melting to water. So basically you are producing entropy, and the amount of entropy that is not producing, there is a change in entropy, but the change in entropy is positive. Again, don't call it entropy. So this is something that I am sorry for, means I have told entropy produced. We should not call entropy produced. It is the entropy that is exchanged, or the entropy that is basically exchanged or transferred between the system and the surrounding. So this is delta S E, or you can call it delta S transfer, means the amount of entropy that is to be transferred to the system for this ice melting to water at 298 Kelvin and 1 bar pressure is 20.15 joules per Kelvin. Now delta S total is basically delta S system, but delta S system, remember, has something called delta SE, that is the amount of entropy that is to be transferred for ice melting to water, and that amount of entropy that is exchanged between the system and the surrounding, because delta S surrounding is nothing but delta S surrounding and delta SE inside the system, right, basically they have to add up to 0, right. So if it is minus 20.15, then there will be plus 20.15, right, this is plus 20.15. But you see delta S system is slightly more than delta SE, because delta S system is given as 22, right, it is 22 joules per Kelvin, right. It was given as the entropy difference between water and ice is at 298 Kelvin is 22 joules per Kelvin. So 22 joules per Kelvin is delta S system, but the entropy that is exchanged is only plus 20.15. As you can see here, this is minus 20.15. So the exact amount with the opposite sign will be transferred to the system, which is minus 20.15. The minus of minus 20.15 is plus 20.15 that will be transferred to the system. But there is a entropy difference which is 22. So if you see, there is the delta S system is 22, which includes this part plus the irreversible part, and for the surrounding there is no irreversible part, right. The process is happening inside the system, right. The irreversible process is happening inside the system. So this is negative 20.15, this is plus 22.0. So you get a plus 1.85 joules per Kelvin. As you can see, it is indeed a spontaneous process, because the delta S total or delta S universe is positive, right. It is indeed a spontaneous process, and the delta S irreversible, right. The delta S irreversible, that is the amount of entropy produced inside the system, is 1.85 joules per Kelvin, right. So basically, as I told you, that delta S system is nothing but it is 22, which is 20.15 plus delta SIR, and delta SIR is 1.85, and if you add them, basically you get 22, right. So basically 22 is 20.15 plus 1.85, and 1.85, that means is the amount of entropy that is produced in the system during this spontaneous transformation from ice to water, right? Now, if you think of delta G, as I told you, this is nothing but the minus T delta S IR, which is basically minus 551.3 joules, right? This is the chemical energy which is changed. This is the amount of chemical energy or this free energy change, or this minus 551.3, right? 298 minus 298 into 1.85 is nothing but delta G, and this is the chemical energy that is changed to thermal energy, right? That is converted to thermal energy, right? So, we will discuss further in the next lecture. We will discuss further about the unary system, the equilibrium in unary system, and we will discuss how to represent this using a phase diagram and the phase boundary, and we will also discuss the concept of there is something called a phase rule to quantify these transformations. So, we will discuss all of this in the next lecture.